Hello, welcome. This is the next FP1 video. This is the start of proof by mathematical induction. Now that sounds very complicated, and what the hell do we mean by mathematical induction? Well, the shorthand is just proving the equation works, okay? Essentially proving that both sides of the equation are equal, okay? And even though, as I said, there are tutorials online, examiner solutions, that make it seem really complicated, and I'm going to hopefully prove to you that it isn't that complicated and try and show you a method that works, and I personally think for me is a lot easier because you're comparing both sides of the equation all the time. You're not just picking one and going with that. Okay, so in this video what I'm going to be proving to you is the sum of r, the sum of r squared and the sum of r cubed, okay? And in other videos I'll be doing other variations, but they'll all follow the same method, okay? The first one I'm going to start with is the sum of r. Okay, and we said that was equal to n over 2 times n plus 1, okay? So, should we do a show? Yep. So the first thing you would do in this situation, first step, call it number 1, is to prove that the equations are actually equal by simply subbing numbers in. Now it's key to remember this is the sum of. Okay, so for 1 it'll obviously just add 1, that's it. When you sub in 1, obviously that's just 1 because it's just r, okay? And then we sub 1 to be n, so 1 over 2 plus 1 plus 1. Okay, so in other words it's 1 is equal to a half times 2, which is obviously 1 is 1, okay, and then you prove it's 2 as well, just sub in 2, and then 2 over 2 times 2 plus 1, okay. Now you think, oh, that comes to 3, well you've got to remember it's the addition, it's the sum, okay, so it's this 2 plus the 1, okay, so therefore that equals, when you add these together, it equals 3, and when you do the sum of that, that also equals 3, so therefore these two are equal. So that's okay. Now that's very good, and obviously you don't stop there. So the next thing you write, this is stage 2, the next thing you write, you have to underline this obviously, you assume this to be true, so you should just put assume true for n equals k. And you can also put r equals k because we've assumed, when we've sub 1 in here, we've treated r the same as n, so you can put n is k and r is k. So all we're going to do is wherever we see r or k, r or n, we're just going to sub in k. But we're still going to keep it sort of split up, but you can the first layer, row on this side is equal to the first row on that side, okay? You can put a little equal sign there, I'm not sure if you can quite see it. Okay, so leave this as the same, okay, so we'll just put k is equal to, we sub k in there, so it's k over 2 where we'd see n, brackets k plus 1, because it'd be n plus 1, we just sub it in n for k. Okay, so we say that's okay. And then the next little bit, so therefore if it's true for k, we assume it's true for k plus 1. In other words, the next term. And obviously that's equal to n as well. So wherever we see k, we put k plus 1 because that's where we'd see n or r originally. Okay, so do it again. So k, but we're not going to just put k plus 1 here because k was the first term, we're adding on the next term. The next term is k plus 1. Okay, so it's plus k plus 1. Even though you tend to put 2k plus 1 there because we just simplify it down, you should really just keep it as a single commodity. Okay, and then on the right, wherever we put n, we put k plus 1, so it's k plus 1 over 2 times k plus 1. And now I know you could just do, therefore you could just say, well, it's k plus 1 squared over 2, but I'd leave it as that for the moment. You could put it all over 2, it might work for you, but just to keep you in mind of that, because what that's really saying is that's saying n times n plus 1 all over 2, which is exactly the same as that. Okay, I'll move that arrow to not make it more complicated. Okay, so that's an okay section. We just proved that this half of the equation, this term is equal to that term, and then you add on the next term, it's equal to the next term of this one. Okay, and the reason why we've not added this to that, okay, like because we've done k over there and then added k plus 1, and we've just inputted k plus 1 over here, remember this is the sum half of it, okay, and this is just the individual term. So to work out the sum of any amount of terms, we just simply sub the number in the right hand side here. But when we sub in the number to the left hand side, we have to add the previous one, because remember this is just the term, okay, that's just the number of the terms. Like when we did this sum and arithmetic progressions, we added the previous term to the next one, okay. So you have to do that, because on the left hand side, I've not really wrote it, but I should have done it here. Draw a little line down going left hand side, and that just means the left hand side of the equation and right hand side. Okay, so that's why I put this little line here. We don't have to, it's up to you. Okay, so that's step 2. And then step 3 really is just, well, it's quite complicated actually. It's combining the two parts of step 2 together. Now we know k is equal to k over 2 times k plus 1. Well, we've got k here, so we simply sub this in, because k is equal to k over 2 times k plus 1 into this k here. And we rewrite all that equation subbed in over here, okay? So we know k is equal to k over 2 times k plus 1, and we've got k here, so we simply sub that in. So it's k over 2 times k plus 1, okay? And then you add the k plus 1, because we've still got it, we're still doing the left hand side, okay? Still bracketed it off. And that's equal to this right hand side thing here, which is k plus 1 over 2 times k plus 1. So it's k plus 1 over 2 k plus 1. Now we know this hand side of the equation is this, the actual sum bit, and this on the side is just added all the individual terms together. So they are the same, okay? Right. So what we need to do is make this left hand side look like this right hand side, okay, of the equals sign. Because this left hand side is, we're showing that each of the terms added together is equal to this sum, just as like the sum of r on the left here is equal to this sum on the right. So that's essentially what we're doing. We've just subbed k plus 1 to be n, and we've got up with this formula. So what we need to do is make this left hand side look like this right hand side over here. Okay, so what you need to do is obviously substitute it down. It's just basic algebra now. So the key bits really are understanding the steps. Okay, but I'll recap the steps a bit later on. Okay, so what we need to do is just simplify that down. So just be a second. Right. Okay, so the next step would be to make this left hand side look like the right hand side, because remember this k plus 1 over 2 times k plus 1, okay, have I done that right? So let me just double check. So it should be k plus 2 on the side, I do apologise. Sorry. Yeah, and that's the same as this n plus 1, where you assume to be n to be k plus 1, okay? So when we convert, we can easily just convert this back by saying, because we put n is equal to k plus 1, we just sub n to be k plus 1. And if we do that, well, we wouldn't get this answer, okay, for both sides. We get it for the right hand side because, well, that's what we've converted, okay? We've just stuck with this, and we'd go back to it, okay? If we just put k to be n to be k plus 1, we'd get the same answer because they are both the right hand side. What we need to do is make this left hand side, which was a sum of r, okay, look like the right hand side. So what we're going to do now, okay, I'm just going to write it out a little bit neater. Okay, so what you might want to do in your next step, I know I'm taking a few steps here, but k times, just make it look a bit nicer, okay? I'm not doing anything mathematical to it, so I'm just putting the k plus 1, which is times by k over 2, on top of the 2, which just means it's part of the same fraction. Okay, I'm just rewriting it in a slightly different way, okay? Plus k plus 1, okay? And that is equal to k plus 1. And I'm going to do the same thing with the right hand side, because it's times by, so it's because k plus 1 over 2 is times by k plus 2, we can just move the k plus 2 to the top, okay, if that makes some kind of sense. Okay, that's over 2. Now, what we've got here on the right hand side, if I'm not going to expand it, but if we did, what we would have obviously is some kind of quadratic. I think it'd be k squared plus k plus 2k plus 2. Okay, so it'd be obviously k squared plus 3k plus 2. Okay, but what we need to make that on the right hand side. But you've got to notice we've got a problem here. This k plus 1 is not over anything. However, if we times it by 2 over 2, we're just timesing it by 1. Okay, so we don't have to do anything else to any other part of this equation. Okay, so we don't have to do anything with this side. So the k plus 1 is still times by k over 2. But we're just timesing this k plus 1 by 2 over 2. Okay, so it's 2 times k plus 1 over 2. So they're all over the same denominator now. Okay, so we can begin and see where we can go from this. We can begin to make it look a bit nicer. Okay, it's k plus 2 over 2. Okay, so what we need to do now is put all of this as one fraction, because that's just one fraction, and then try and simplify it. Okay, so obviously it's k times k plus 1 plus 2 brackets k plus 1, and that's all over 2. Okay, and that's equal to k plus 1 k plus 2 over 2. So what we're going to do now, because obviously this is going to factorise, sorry, this is going to expand to a quadratic, so this should factorise like that one does. In other words, we can't factorise that straight away, so we need to make that a quadratic and then factorise it, okay? So to make it quadratic, we just expand all the terms out and see where we go. So if you expand the first bracket, obviously you get k squared plus k. If you expand the second bracket, you get 2k plus 2, and that's all over 2. And we say that's the same as k plus 1, k plus 2, all over 2. Okay? Right, so on the left hand side here, what we've got to do is now simplify this. Well, obviously we've got k plus 2k is what we can simplify, so we just simplify that to plus 3k. Now as I said, that factorised, the expansion of k plus 1 times k plus 2 expands to k squared plus 3k plus 2. Okay, so quite clearly that factorises to k plus 1, k plus 2. So therefore we're saying k plus 1 times k plus 2 over 2 is equal to k plus 1 times k plus 2 over 2, which is exactly what we want. And then you can just split it up again and simplify it down. Okay, so you would have k plus 1, k plus 2. And because the left hand side equals the right hand side, we can say it is now mathematically proven. But you do need to make it look, you do need to make both sides sort of look like that. Okay, so okay, so it's just a case of splitting it up and making it look like n over 2 times n plus 1. Okay, and it says just a case now, so all you would do, okay, to just finish it off, just me double check and go in bunkers. So I do apologise, one sec. Yep, so because it's because we said n is equal to k plus 1, just so n to be k plus 1, okay, so it's n over 2 times n plus 1, okay, and that's the same for both sides. So you say the left hand side equals the right hand side, so all we've done is this, the left hand side is the sum up, and the right hand side is just a manipulation of the original equation, okay, which we were told, and we had to prove it. Okay, so that's the answer there. So, as I said, all we've done, really, the principles of this, okay, so just give you a second to copy that down. You want to pause the video because I'm just going to put kind of a pointer up of how to go through answering this question. Okay, I might leave the answer there in this little bit, but I'm just definitely going to get rid of this bit here, okay, so Alright, okay, so what I'm going to do now, as I said, I'm just going to give you, it's not really a very good method, to be honest, but it's kind of just some principles that you need to follow if you were working, if you were proving the sum of something out. That's key, this only works for the sum. Well, this particular method anyway, in terms of, okay, so the first step that you would do is you would split it up into the left hand side and the right hand side in terms of I'm not going to write that down as a first step, but I'm just hoping that's naturally what you do, okay? So, actually I put it in step one, split up into LHS and RHS. Okay, so essentially that just means that put the R and the n over 2 times n plus 1 on two sides, just put a line between them. And I'm going to write in the same step and prove that the sum of 1 and 2 works or gives the same answer for both. Works for both sides. So that's the left hand side and the right hand side. So all I'm doing there is that little bit there, okay? Both sides. The second, okay, is this assume true for n equals k and therefore n equals k plus 1. Okay, so it's the assume, I'm just going to label it as the assume true bit, where you sub in n equals k and then n equals k plus 1. Okay, and then the third step, well, said you kind of need a little bit of a I might confuse you here by my wording, because I'm trying to make it in terms of steps, but it's not really. It's kind of quite. It's the same method, but it's slightly different for different ones. Okay, so then the third step is using the. Well, I'm going to label it as the equation, and what I mean is that bit there. Assume using the. I'll put it in brackets. Using the equation, because it isn't really an equation, it just says that's equal to that. Well, it kind of is, but it's not like the sum equation. Okay, it's just the equation that you came up with, making the left hand side equal to the right hand side when you said assume true for n equals k. So using the equation for n equals k, sub in to n equals k plus 1. And hopefully what you get, what I mean by that is, well, obviously this is equal to k, we've got k down here, so you just sub it in to that k there, okay? Yep, hopefully that makes sense. And then the fourth point would just be to make the left hand side look like the right hand side. And then kind of the fifth point really is just about making it look like the original sum equation. Make both sides look like the original sum equation that you're trying to show. Look like the original sum equation. What you're trying to show. Okay, so that's kind of a rough idea now. Kind of the steps that you should really kind of have in your mind. Now, I've done it for the sum of r, and we're going to do it for the sum of r squared and the sum of r cubed. And if you follow this method, okay, in terms of the steps, and pretty much the same method, it's just a slightly different equation, but the method stays the same, okay? And it does for all sum equations, okay? So all we have to prove by mathematical induction, the sum of something is equal to whatever it is. You follow exactly these methods, okay? But obviously when we're doing the proof of matrices and powers, we do a slightly different principle, but the methods, the steps involved in each mathematical induction are very, very similar in terms of, you know, you make it, you prove that it is equal for whatever, the first few parts of the sum or whatever equation it might be, and then put it true for n equals k and n equals k plus 1, and then make the left hand side look like the right hand side and simplify down to make it look like the original. But these steps are, the ones that I've written down are more geared towards the sum, okay? The principle would work for any proof by induction, but these particular steps, okay, so such as step 5 definitely would only be applicable to sum. So if you can just imagine these just to do with the sum, proof by mathematical induction to do with the sum of a series, okay, that should be fine. And I'll introduce a more tailored steps to the proof by integer powers and power or whatever it is, and then proof of matrix expansion, okay, and multiplication even. Okay, so if you remember, them steps are purely to do with the sum of a series. So what I'm going to do now is just give you another minute if you want to copy them down, and then I'm going to go on and we're going to look at the sum of r squared and r cubed. Okay, so as I said, if you note them points down, and then I'll give you a few seconds at the start of the next little bit, and you can have a go at seeing if you can use them steps to answer the question by yourself, and obviously I'll go through it as well. Okay, so hopefully you've had a go at noting them down. I've just paused the video now. Hello and welcome. Now this is the next little bit of the video. Okay, so in this video I'm going to be proving that the sum of r squared is equal to n over 6. Well, it's not in this video. It's not a new video, it's just an extension of the old one. Anyway, okay, so it's n over 6 times n plus 1 times 2n plus 1. Okay, so we follow the same principles that I put on the board before. So I put them, I think it was 5 or 6. So you start, the first thing that you do is you prove that these are equal, okay, for the first few terms. Okay, so you just always pick 1 and 2. So you put, obviously, you split it up to the left hand side and the right hand side. Okay. And obviously the sum of 1 squared, well, that's 1. And then you put 1 into n, so it's a 6th times 1 plus 1 times 2 times 1 plus 1. Okay, which is obviously just therefore 1/6 times 2 times 3. Okay, which is obviously just also equal to 1. And then you do the sum of 2. You do 2 squared, which is obviously 4. Okay, and then the sum of 2 squared, for according to the left hand side, you add 1 squared plus 2 squared together. Okay, which gives you obviously 5. Okay, and then you put n to be 2 in here, so it's 2/6 times 2 plus 1 times 2 times 2 plus 1. Okay, which is obviously equal to 5. Okay, so hopefully that makes a bit of sense. Okay, so the same principle, you say therefore they're equal. And as this works, the next stage you says you assume it's true. So you write the same thing. Assume true for n equals k. Okay, in other words, you just sub n to be k and r to be k on the left hand side. Okay, so you still do left hand side, right hand side. So it's k squared, because that's obviously r squared to k squared, and put that in equal. Okay, to k over 6 k plus 1 2 times k plus 1, so it's just 2k plus 1. Okay, right. So when you've done that, you do the new line. Okay, so you assume true for, sorry, I'll move out of the way in a minute, for n equals k plus 1. Okay, and you do the same principle. Okay, but remember, you don't just put, because this is r squared and not just and not just r plus r plus r. Okay, we have to square the k plus 1. We have to square the whole thing. So when we add k plus 1 onto the second part here, so in a sec, just double check. I'm just double checking something. Yeah, so we do k squared and then we do k plus 1 all squared. Okay, and then we just, on the right hand side, we just replace where we've got k with k plus 1. In other words, replacing n with k plus 1. So it's k plus 1 over 6. And then because it's just, it looks like we've already got k plus 1 there, but remember this is n plus 1. So obviously if it's n plus 1 and we're assuming n is k plus 1, well it's k plus 1 plus 1. So it's obviously just k plus 2. And then on the and then for the 2n plus 1, we said n is equal to k plus 1, so it's 2 times k plus 1 plus 1. Okay, so obviously that's you've got 2k plus 3 that comes to. Okay, so the next step was subbing this here, so the k squared, into that k squared there, and sort of doing a new line of working for that. Okay. Okay, so you just input k squared into that k squared there and keep them as equal. Okay, so we say k squared was k over 6 times k plus 1 times 2k plus 1. Okay, so just sub that in for k squared, so k over 6 times k plus 1 times 2k plus 1. And we add to that k plus 1 all squared. Okay, and we say that, so same as the right hand side, which says k plus 1 over 6 times k plus 2 2k plus 3. But just like before, that is k plus 1 over 6 times by k plus 2 times by 2k plus 3. And it applies to the similar principle on the other side as well. So we're going to need to knit up and put it all over the same denominator where we can. So it's k times k plus 1 times 2k plus 1. So all over 6. And we just simply add k plus 1 all squared. That's not over anything yet. Okay, and we make that, we say that equal therefore to k plus 1 times k plus 2 times 2k plus 3. Okay, and that's all over 6. Okay, so we've got to make this left hand side here look like the right hand side here. Well, you'll spot straight away that obviously this is over 6, but the add obviously k plus 1 all squared is not over 6. So what we need to do is times this by 6 over 6. Okay, I'm going to sort out this little bit here later on, because obviously we're going to need to do something to that in a minute. Okay, so just leave it as it was, so k times k plus 1 times 2k plus 1, so all over 6. And then we just times the k plus 1 all squared by 6 over 6. In other words, we're timesing it by 1. Then you go, well, why aren't we timesing the other one by 6 over 6? Well, that'd be pointless because we've times that by 1 and it's not affected the values of anything else, so we don't need to times it all by whatever. Okay, it's only if we're just timesing that by 6. We're not. We times it by 6 over 6, which is obviously 1, so don't get that confused in your mind. So 6 times k plus 1 all squared over 6 is equal to k plus 1, k plus 2, 2k plus 3, and that's all over 6. Okay, so we've got a common denominator on both sides now, so we can just expand that and put it together with that one expanded all over 1 equation. I do apologise, I've got a bit of a cold, but never mind, we'll man through it. Okay, so you can do a k plus 1 all squared, depends what you want to do next actually. I've probably not left enough room to expand them all and continue to finish this off. So just to let you know, because I've done the calculations, k plus 1 all squared, well obviously it's k plus 1 times k plus 1, okay, which is obviously k squared plus 2k plus 1, but because we've got 6 times k plus 1 all squared, we times that all by 6, so obviously we get 6k squared, 12k plus 6. Okay, and so that applies to this 6 brackets k plus 1 all squared. Now we need to expand all that because, well, if you look, we have got a k plus 1 there. Actually, could we do that? One sec, actually I'm just going to have a go, because I've got it on my, because I've done the answers previously. I've done it a slightly different way by expanding this. Okay, the k plus 1 times 2k plus 1, but we've already got k plus 1 as a factor over on the right hand side, so maybe there's no need to expand them too, but I'm just going to double check and I'll come back in a second. Sorry, I just thought I'd have another attempt at trying to do it a different way, but obviously when I had a go at that, for some reason it didn't work. Now maybe that was because I didn't calculate it right, or I didn't expand it, but This way I'm going to show you now does work. I just tried a different way because I thought it'd be a bit easier, but turned out I made it complete. I probably did something you weren't allowed to do. Anyway, okay, so what you would do is I've expanded to 6 times k plus 1 all squared and got 6k squared plus 12k plus 6. Okay, so you can just replace that with the 6 times k plus 1 all squared. Now the thing to do, I was spotting, I said, well, we've got this k plus 1 and surely we can do something like, you know, expand k times 2k plus 1. But obviously you can't do that because these two are double brackets and it would make it a bit stupid. Okay, so what we're going to do instead, I know this sounds stupid because you see k plus 1, well that's already a factor in what we're trying to get it to look like, so why do we want to mess around with that? What we're going to do is expand all of this. We've essentially expanded this 6 times k plus 1 all squared to get you 6k squared plus 12k plus 6. Okay, so we're going to expand this left here. Okay, so I'll take k out because obviously we need to expand the double brackets first. So k times 2k is obviously 2k squared plus 3k plus 1. Okay, and obviously that's all times by k, and then we add to that this 6k squared plus 12k plus 6, and that is all over 6. Okay, and we need to make that equal to whatever this is, so k plus 1 times k plus 2 times 2k plus 3 all over 6. Okay, so what we're going to do is expand this k business on the left hand side here. So what we're going to do is, as I said, just simply expand it and keep it as all over 6. So obviously it's k times 2k squared, k times 3k, and k times 1. Okay, so obviously that's 2k cubed plus 3k squared plus k, and we add this to the 6k squared plus 12k plus 6, and I said still all over 6. Okay, and we want to make that equal to this function on the right. I'm just going to put an x there, well, not an x, put a little star because I can't bother writing it out again. Okay, so simplifying all this down now. So obviously we've only got one lot of k cubed, so it's 2k cubed. We've got k squared, there's 3k squared, 6k squared, that obviously leaves us with 9k squared. Okay, and then we've got k plus 12k, well that obviously leaves us to say, well, plus 13k. And then we've just got the lonely plus 6 on the end. Okay, so what we need to do is factorise that to make it look like k plus 1, k plus 2 times 2k plus 3. Now you can't just say, oh well, it's equal to each other, so there we are, we've solved it. Well, we haven't. We haven't proved that 2k cubed plus 9k squared plus 13k plus 6 is equal to that factorised form on the right hand side there. Now, we should know because we've kind of proved it here already. You could prove it by saying, well, k plus 1 or using 2k plus 1. You know that is a factor of this. I'll choose k plus 1 because it's easier. We know k plus 1 is a factor of this cubic. Now going back to, as I said, C2 knowledge, how to factorise a cubic. Obviously this cubic is made up of a quadratic and a non-linear function. Sorry, a linear function even. Okay, linear function being k plus 1. Now, as I said, you could either use the 2 plus 1. Now, as I said, sorry. It was made up of a quadratic and a linear, and also you can split that quadratic, as we can see, into 2 of the linear. So essentially it's made up of 3 linear factors. But we only know for certain that k plus 1 and 2k plus 1, they are factors, okay? So what you could do, just to prove to the examiner that obviously k plus 1 is a factor, you go, because if we want k plus 1 to be a factor, we need to know what k is in that to make this 0. Okay, so if f is minus 1, because obviously we want to know what k is in k plus 1, then we make that 0. Well, therefore, obviously, k is minus 1. So therefore, f of minus 1, and you put that in, you'll get that to be 0, okay, into this cubic. And then when you do that, okay, you can therefore say, well, therefore k plus 1 is a factor. Now, we already knew that, but just to reiterate, so the examiner follows you working, because you can see my method's kind of stupid. Now, what we've got is a factor, and we've got sorry, my brain's just gone funny. We've got a cubic here, and we've got a factor of it. So we just use the factor theorem. That's factor and remainder theorem, okay? So we're going to use algebraic long division. Okay, so we take the k plus 1 out as a factor, okay, and we're going to divide that by 2k cubed. So we're going to divide 2k cubed plus 9k squared plus 13k plus 6 by this k plus 1, okay? And then when you do that, you will end up with a quadratic on the top here, okay? I'm not going to do it because I kind of don't have enough room, but hopefully you know the process of algebraic long division. So you divide 2k cubed by k, okay, which obviously gets you your 2k squared, okay? And then you times that by 2k, k plus 1 by 2k squared, and take it away from this equation and repeat the process and again and again. But as I said, if you don't get that, please do check out my algebraic long division video, but I'm hoping you get how we would get the quadratic here, okay? So we get a quadratic, alright, so it'd be 2k squared plus 4k plus 3k, which is obviously 2k squared plus 7k plus 6, okay, which obviously factorises to k plus 2, 2k plus 3, and we know k plus 1 is a factor, so therefore the factors of this are k plus 1, k plus 2 and 2k plus 3. Okay, so we know they are factors of this, so you can just input them factors into there, and we know that, we said that n is equal to k plus 1, so obviously you could sub it in, your n, so it'd be n plus 1, and then obviously you could rearrange that as needed. Okay, and then you just simplify it down, so we do it in terms of n. Now I don't quite have enough room, but I'm hoping you get how we do that. So just sub these factors into that, and obviously you would make it look like this, okay, by just subbing n to be k plus 1. As I said, if you want me to add a little bit more to this video of how to finish that off, please do let me know, but I'm kind of hoping that it's self-explanatory there. Alright, so thanks for watching. As again, sorry for not kind of finishing that question off. I kind of ran out of room, but I didn't want to start rubbing bits off and moving stuff around, okay? So as I said, if you do want me to add a bit more onto the video, actually, should I? I don't know if I might do it now. Yeah, I'll do it now. Just tidy the board up. I just changed my mind. This is how spontaneous these videos are. I'll change my mind actually. So if you have a quick note of that, and then I'm just going to rub off this section here, okay, because it's the least mathematical section, and replace it by sorting this out to make it look like what it should do. Okay, so I'll just give you a second now to have a go at that. Sorry, have a copy down of that if you've not done already, and then I'm going to move on to the next little bit. To simplify it down. Okay, so hopefully you've done that. I'm just going to simplify it now. Sorry about that. So I was thinking about not adding this in, but then I kind of changed my mind because I thought, well, it's quite important really, and obviously you need to be able to do it to finish the question, so I just thought I'd add it in, to be honest, because you know, it's not that difficult. Okay, so what we know, we're going to take the inspiration that n is equal to k plus 1 to sub in for n, okay, because that's essentially where we've got up to, and we need to go backwards from that. So as I said, we know what k is, so we're just going to sub the n back in there. Okay, so we know n is equal to k plus 1. So the first thing we're going to do now, I'm not going to continue with this right hand side now, because they're equal to each other, so you can be done with both sides. Okay, so anyway, as I said, n is equal to k plus 1, so obviously the first term is n, and then it's n plus 1. Now this next term, 2k plus 3, we just have to think, well, what did we do to get 2k plus 3? We said n was equal to k plus 1, so therefore it's literally just 2n plus 1. Okay, we said that's all over 6, and then you just make it look like it does over here. Okay, so it's n over 6, n plus 1 times 2n plus 1, and that is where you would stop. You'd say therefore it is proven. Okay, so the same principles apply of proving that it's equal to for values of 1 and 2. Assuming it's true for n is k, then n is k plus 1. Simply subbing it in when you see r or n, k, and then k plus 1. Okay, remember to add the term for the left hand side because that's just simply the value of each term. Okay, so r squared is just the formula at 2. Okay, whereas the right hand side is the sum of the formula at 2, so we don't add on the extra k plus 1 on that side. And then it's just a case of making it, and then it's just a case of where you've got a assume true for n equals k, subbing that into this, the second little bit of the left hand side, okay, and making then when you've done that, make the left hand side look like the right hand side, and when you've done that, simplifying both down to make them look like that on the right hand side there, and then you just put a little sign saying proof, okay. But it is true to put, sorry, it is vital to put these two assume true for n equals k and n equals k plus 1. What that means, as I said in the previous little bit, is just that's one term and that's the next term. Okay, k plus 1, k just being a number, a term, okay, should be term 3, term 4, whatever it may be, and then it's the next term. Okay, so hopefully, as I said, that makes a little bit of sense. Okay, so just going to rub all this off now, and then we'll go on to look at proving the sum of r cubed. Okay, so just be a second and I'll rub all this off and we'll move on to r cubed. Okay, so this is the next little bit, proving the sum of r cubed. Now, as I said, we're going to follow the same method that I followed for the sum of r and the sum of r squared. This equation here, you'll note, is the equation of r, which is n over 2 times n plus 1 all squared. Sorry, times n plus 1. And it's the sum of r, but it's squared, even though it's the sum of r cubed, so it's kind of weird. If you can imagine, it's the sum of r times the sum of r squared, like the two powers of r give you r cubed, so hopefully that's a way to remember this equation, but just remember it's the sum of r squared, but it's not the sum of r squared. I probably just made something up there. Anyway, okay, so prove the same thing. So on the first step that we talked about, we'll split it up into the left hand side and the right hand side, and prove for the sum of 1 and 2, it works for both. So the sum of 1 is just 1 cubed, that equals 1. And on the left hand side, 1 squared over 4, 1 plus 1 squared. Well, that's obviously 2 squared, which is 4, so 4 times quarter is 1. Okay, and then you do 2, well that's 2 cubed, that's 8. But remember, this is just the individual terms, the number of the individual terms. Okay, so it's 1 plus 8, so therefore the sum of 2 should be 9. So this equation on the right should prove that. So when we have n to be 2, so 2 squared over 4, 2 plus 1 all squared, okay, which obviously just gives us 9. Yeah. Done that right? Yeah. Okay, so hopefully you can see that, because obviously that's just 2 squared is 4. 4 over 4 times 3 squared is obviously 9. Okay, so you say obviously they're equal, so it works. The next little bit you need to do is assume true for n equals k. And as I always mention, this is literally just subbing in n to be k or r to be k, wherever you see n. Okay, or r. So on the left hand side, we're going to do the same thing. Well, we've got r cubed, so we're going to put k cubed instead, so it's k cubed. And on the right hand side, we've got n squared, which is obviously k squared over 4 times k plus 1 all squared. Okay, so if it's true for n equals k, then it's true for the next value as well. You assume it to be, so you put assume true for n equals k plus 1. Okay, so literally, because this is the sum, remember, on the right hand side, and we've just got the individual terms on the left hand side, so we need to add the individual terms together on the left hand side and simply put k plus 1 into the right hand side. Okay, so it's k cubed, but it's not just k cubed plus 1, it's k plus 1 all cubed, as we did when we did the x squared, k squared even. Okay, and then on the right hand side we just sub in k plus 1, so it's k plus 1 all squared over 4 times k plus, well, it's not k plus 1 all squared because that's the same as k equals n, or n equals k, so it's k plus 2 all squared. Okay, and then the next step, well, we take it all the way up here again, and we simply sub in that the k cubed is equal to k squared on 4 times k plus 1 all squared into this k cubed over here, and take the right hand side as well up over here and make them equal. Okay, so we said k cubed was the same as k squared over 4 times k plus 1 all squared. Okay, and we add to that k plus 1 all squared as well. Okay, and we make that look like the right hand side, which says that is equal to k plus 1 all squared over 4 times k plus 2 all squared. Now it's just a case of making this left hand side look like the right hand side. But what I always suggest, and I've done this in the previous sums that we've gone through, is giving them all a common denominator, or simplify them, so you put them all over a common denominator. Okay, so well obviously over here we've got k squared times k plus 1 all squared, and that's all over 4. But the k plus 1 all squared, when you add that, this second k plus 1 all squared, well that technically isn't so this k plus 1 all squared is times by the k squared, whereas this k plus 1 all squared is come from the addition over here. Okay, so, oh sorry, that's not squared is it, at all. Stupid look. It's k plus 1 all cubed. Sorry, I do apologise. Yeah, because it's the next term cubed, because that's the sum of r cubed. Sorry, I do apologise. So it's k plus 1 all cubed. I didn't think that was right. So I do apologise. It's equal to k plus 1 squared over 4. Sorry, k plus 1 all squared times k plus 2 all squared, and that is all over 4. Okay, so we've got two of these that are over 4, so obviously we need to give them all a common denominator, but we can't do anything to one side that we don't do to the other. So essentially, because we just need to times this, give this a denominator of 4, we need to times it by 4 over 4, because that's, as I said, the same as times it by 1. Okay, and then it will all have a common denominator. So k squared times k plus 1 all squared over 4 plus 4 times k plus 1 all cubed over 4. Okay, it's equal to this k plus 1 squared times k plus 2 squared. That is all over 4. Okay, so what we need to do now is make this left hand side. I said we keep the theory of making a left hand side look like the right hand side. Well, personally, it doesn't matter which order that you expand these two in, obviously. Well, personally, because we've just expanded this k plus 1 all squared, not in this part of the question, in a previous sum, it's quite easy to remember. Okay, so remember we said that the sum of k plus 1 all squared, sorry, it's not a very good example there, is obviously, well, you get k squared plus 2k. Is that right? Yeah. Sorry, sometimes I just doubt myself just because I can. Yeah, k squared plus 2k plus 1. Okay, so sum of k squared, k plus 1 all squared, and obviously we're timesing that by k squared. Okay, so all of this by k squared. Okay, so we're going to put that over here. So it's k squared plus 2k plus 1, all times by k squared. Well, obviously the k squared times the k squared, it's going to give us k to the 4, and k squared times 2k, well, that's obviously going to give us plus 2k cubed, and then the k squared times 1, which is going to give us k squared. Okay, and so that's over 4, and then we add that, we're going to expand this bit, but we need to know the expansion of k plus 1 all cubed. So it's k plus 1 times k plus 1 times k plus 1. Okay, so when you get a triple bracket, you just expand one. Okay, just expand the set of double brackets and then use that answer and times it by the third bracket. Okay, so we know what k plus 1 all squared is, so k plus 1 times k plus 1. Okay, which we just said was your k squared plus 2k plus 1. I'm going to times it by k plus 1. Okay, so it does start to look a bit messy, but I mean, hopefully you can see where we're getting all this from. So obviously I'm just going to times them all by k. So k squared times k, 2k times k, and 1 times k. So obviously your k squared times k, that's going to give you k cubed. Your 2k times k is obviously going to give you 2k squared. And your 1 times k is obviously going to give you k. And then we times all of it by 1, because we times it by k, now we need to times it by the plus 1. Okay, so that actually just gets us k squared plus 2k plus 1. And then we're going to simplify that. Okay, so obviously we've only got 1k cubed there. So it's k cubed We've got 2k squared, so we've got 2k squared plus k squared, so obviously plus 3k squared. And then we've got 3k plus 3k plus 1. Okay? So that is the expansion of k plus 1 all cubed. But because we've got it times by 4, we need to times all of this by 4. Okay, so all I've done so far in this word, loads of crap, is just expanded this k squared times k plus 1 all squared, and I've just expanded this k plus 1 all cubed, and then I need to times it by 4, all of that, to get the answer. Okay, so when we times it by 4 to get the answer, 4 times k plus 1 all cubed, you get 4k cubed plus 12k squared plus 12k plus 4. Okay, so that's your answer to 4 times k plus 1 all cubed. Okay, so you sub that in to that part of the equation. Okay, so it's 4k cubed plus 12k squared plus 12k plus 4. That's all over 4. Now don't be tempted, I know you can do, to divide all that by 4, but you'll just end up with what k plus 1 all cubed was, and that's pointless, okay, because that doesn't help us at all. We could have just done that there. We did this for a reason, okay, so don't be tempted to divide it all by 4, even though you can do. Okay, that's equal to k plus 1 all squared, times k plus 2 all squared, all over 4, okay, so just need to rub that out there at the bottom thing, because hopefully you get how we expanded k plus 1 all cubed, but I mean I just did it, so I knew where I was going with this, but hopefully you already knew that. Okay, so we're both over 4, so we can put all of that over one fraction now, like the other one, and we can see what we can do from that. Okay, so what I'm going to do now is just kind of finish this off. I've added in, what I've done here is I've just paired these two, sorry about that line, I've just put these two together, okay, in terms of, I've put them as one fraction and cancelled them down, so we've got k to the 4 plus 6k cubed, plus 13k squared plus 12k plus 4 all over 4, and that we said that's equal to the right hand side of k plus 1 all squared, k plus 2 all squared all over 4. Okay, now to get this quartic, that's what it is, into this form, we can't just simply say, well it's equal to each other, so we'll just put it and we'll just cheat and skip out a load of steps. Well, I'm sure there are different ways of doing this, but the way that I'm going to attempt to do this, I personally think it's the easiest. It might be a little bit of a long way around really, but as I said, it's the easiest, and if you do it right, it shouldn't take you too long. Okay, so what I'm going to do, because I need a bit of room for this obviously, I'm just going to rub this out. So hopefully you've got this down, okay? So I'll just give you a second to give you the left hand side of the board, so this LHS, RHS, the assumed true bit. I'll give you a second to just pause the video and copy that down, and then I'm just going to be explaining this little bit here. Okay? Right, so hopefully you pause it, and now we're just going to factorise that on the left there. Okay, so what we want to do is get the left hand side, i.e. this quartic, looking like this. Now I'm going to ignore the divide by 4 signs for the moment. I'll put them back in later on, or you could keep them in, but personally we need to make this quartic look like this. Now quite clearly that's a quadratic, but you see both factors of the quadratic are squared, so that's going to give us a quartic, so we've not done anything wrong here. Okay, so in other words you could write this k plus 1, we'll write this quartic out, so it's k to the 4 plus 6k cubed plus 13k squared plus 12k plus 4. And we know that is equal to k plus 1 all squared times k plus 2 all squared. Now, this k plus 1 all squared just means k plus 1 times k plus 1. So we'll write that because that looks a bit easier. So k plus 1 times k plus 1 times k plus 2 times k plus 2. Now at this stage, you just to prove to yourself that you've done everything correct. If you're not 100% sure on that, then do expand these 4 brackets in terms of expand that as a quadratic, and then times it by k plus 2, and then times the whole of that by k plus 2 again, and it should get you this answer. I have done it, it does work, so this statement is correct, okay? But obviously we can't just state that, we need to do something with this. Well, these are factors, okay, of this quartic. And if they are factors, we can say you know, if k plus 1 is a factor, because of the two factors of k plus 1, it's a repeated factor. Okay, so we could have it as two factors of this as well. Okay, so if k plus 1 is a factor, we let then f of minus 1 will equal 0. And you can prove that to yourself. Put minus 1 to be k and sub it into this quartic here, and you'll get an answer of 0. So therefore, if k plus 1 is a factor of this, we know a factor of the quartic, just like a cubic, okay? So if you could imagine this was a cubic, we'd do exactly the same thing, algebraic long division. So we know k plus 1 is a factor, so you put k plus 1, and we're going to divide the whole of this quartic by k plus 1. And the answer, the quotient on top, will give us what we times by k plus 1 to get this quartic. In other words, another factor. It's going to give us a cubic, but then we're just going to repeat this, and I'll go on and on. Okay, so we just put the quartic in here, so k to the 4 plus 6k cubed, so it should be a bit more obvious, plus 13k squared plus 12k plus 4. Okay, so we divide k to the 4 over by k, okay, so that obviously gives us k cubed, and then we times k plus 1 by k cubed, okay, then take that away, so it becomes k to the 4 plus k cubed. Okay, so then we just take that away from the quartic and repeat this again. Okay, because obviously we've still got a few more factors we need to include there. So that leaves us, so let's just write this out again. But obviously the k to the 4's cancel, so we're just left with 5k cubed plus 13k squared plus 12k plus 4. And when we divide 5k cubed by k, okay, well it gets us 5k squared. So that's the next part of the quotient. So it's, the quotient so far is k cubed plus 5k squared. Okay, and you do the same, you times k plus 1 by your 5k squared, okay, which gets you 5k cubed plus 5k squared. And you take that away, because obviously it should equal 0, by the way, if this is a factor. You can keep going. Okay, so we do the next line of working. Obviously you do this a lot faster in the exam than I'm doing, I'm just trying to talk through it. And you take the 5k cubes away, so they cancel, and then 13k squared, take 5k squared, that's obviously 8k squared, plus 12k, plus 4. Okay, and then you repeat the process again, so you divide 8k squared by the k, which is obviously just plus 8k. Okay, and then you do the same in terms of you times k plus 1 by 8k, which gives you 8k squared plus 8k. Okay, and you take that away as we have done, and obviously that's because it's only needs a bit more, so you repeat this process. Okay, so k plus 1, and obviously the 8k squares cancel. Okay, so that leaves us with 4k plus 4, and then we divide 4k by k, okay, which obviously just gets us plus 4. Alright, and obviously therefore that leaves us 4k plus 4. We take that away from 4k plus 4, we get 0, so k plus 1 is a factor. Okay, so this is a quotient, k cubed plus 5k squared plus 8k plus 4, and the other factor is k plus 1. But that's not looking like all of these factors. We've got k plus 1 as a factor there. Okay, so, and what we need to do, again, because this cubic does not look like 3 linear factors, we need to split that up into 3 linear factors. Well, again, if what we do the same again, because we've counted off that one of the factors is k plus 1, but there's another factor that's k plus 1. So we repeat this process, but instead of dividing the quartic by k plus 1, we know that this quartic can be transformed into the k plus 1 and this cubic, okay? We can repeat this process, but instead of having the quartic there, we can put this cubic there, and we'll get a quadratic, okay? So hopefully that makes sense. Just going to rub this out and then just reiterate what we've got so far as the factors. Now this may be more confusing than other ways, but as I said, just the way I do it. Okay, so what we've got now is this quartic, okay, is equal to this cubic, okay, which is k cubed plus 5k squared plus 8k plus 4. And when we times that by k plus 1, we get that quartic. So these two are factors. Okay, but we know a factor of this, because we've used k plus 1 as one of the factors, that is a repeated factor, so we can use it again as another factor to work out the quotient of this division, okay? Now, as I said, it might be confusing you completely. Basically, what I'm trying to do is repeat this algebraic long division, and I can do k plus 1 again because we've got two factors which both are k plus 1. In other words, a repeated factor over here. So we can repeat this process, okay? Now we know the cubic is a factor, and that's great, but what it's going to give us is, well, one of the factors we know is k plus 1, and it's going to give us k plus 1, and then k plus 1 again, because we've done the algebraic long division twice, and this quadratic, which it will give us, and then they are three factors of this quartic, which we're trying to find. And the reason we're trying to find a factor of this quartic is because we're trying to make this make sense. Okay, we're trying to prove that by making this quartic, okay, have the factors of k plus 1 squared all squared and k plus 2 all squared. And to have that, we need to show that k plus 1 all squared is two factors of k plus 1. So k plus 1 times k plus 1 is k plus 1 squared. So therefore we've got two factors that both say k plus 1. Okay, so that's why we can do this algebraic long division twice. So repeat the process, okay? So it's k cubed over k, which gives us k squared. Okay, and then we times k plus 1 by k squared, which obviously gets us k cubed plus k squared. And we take that away, okay? Well, obviously that's not going to finish the algebraic long division there. So we need to repeat this process again. So we take that away, okay? So we get 4k squared plus 8k plus 4. Okay, and repeat the process. Well, you divide your 4k squared by 4k, okay, which obviously just gets you 4k, so it's k squared plus 4k. And obviously you times all of that, k plus 1 by 4k, which obviously gets you your 4k squared plus 4k. Okay, and then obviously when you take that away, it's not going to give you this 0, so you need to repeat the process because we can. Okay, so 4k squared, take 4k squared, it's going to nothing. What we're left with is this 4k plus 4. Okay, so repeat the process. So 4k over k, which is going to give us plus 4. Okay, so that's your quotient. And obviously when you times k plus 1 by 4, you just get 4k plus 4. And obviously that, when you take them two away, that leaves you with 0. So therefore k plus 1 is also a factor of that. Hence it's two factors of this quartic. Okay, so what we've got now so far is we've got two factors of k plus 1, and we've got a factor of k squared plus 4k plus 4. And that must factorise, if this is correct, to k plus 2 all squared, because two of our factors are k plus 1, so k plus 1 squared. So the other factor, which is the other factor in this, okay, which is k plus 2 all squared. So this quadratic must be have a repeated linear factor of k plus 2. Okay, so what I'm going to do now is just rub this out so it makes sense of all the factors we've got so far. Okay, so I know it only looks we've got k plus 1 once there, but we've done the algebraic long division twice and proved that k plus 1 is a factor of this quartic and the cubic. Okay, and the cubic is just this the part of this quartic where we've taken out k plus 1 as a factor. Okay, so just read out the factors we've got so far. So this quartic, so k to the 4, etc., etc. I'm going to write it all out. We've got k plus 1 as a factor, and we've got k plus 1 also as another factor, because we've done algebraic long division twice, and they both come to 0. Okay, so k plus 1 is a repeated factor. Okay, and we've also got this quadratic as a factor of this quartic. Okay, so really these two combine. Okay, to give us k plus 1 all squared, but we'll get to that in a minute. Okay, so we need to do something with this quadratic to make it look like a linear factor. Now there's a number of ways you can do this. You can go just straight to it, because an examiner will see that you're obviously able just to deduce that that is a linear factor, two linear factors repeated. Or you could do the quadratic formula, but I'm not going to do that because I'm hoping you see that. Okay, so again this quartic, now I'm not going to write it all out again because it's just this one here, okay, is equal to k plus 1 times k plus 1 times k plus 2 times k plus 2. Now these are repeated factors, and so are these. Okay, so we can just make this quartic again equal to k plus 1 all squared because it's a repeated factor, and k plus 2 all squared is a repeated factor. So therefore we've proved that this quartic is equal to k plus 1 all squared times k plus 2 all squared, which you can just replace over here, so therefore they are equal. Alright? So hopefully it's making sense. I thought that was kind of the complicated bit really, but it's just using C2 methods. Alright, so now that we've said these two are equal because we've replaced this quartic with the factors that we want, okay? So we can just go from here. And all you need to do now is when you've got the k plus 1 all squared times k plus 2 all squared over 4 is make it look like this, okay? And so therefore what you would do, well obviously we said let n equal k plus 1, okay? So you sub k plus 1 to be n, or n to be k plus 1, so it's n squared times, well obviously k plus 2 is, is n plus 1, okay, so it's n plus 1 all squared, and that is all over 4, and you just break that up to make it look like this formula I'm trying to get, so it's n squared over 4 times n plus 1 all squared. Okay, so now you would put proof. Now, as I said, I personally think that's probably a bit of a long way to do it. If you've got any quicker ways, please do let me know, but that really works, and I think basically just using algebraic long division. I'm not plucking numbers from somewhere you don't know, and personally, if you were in the exam and didn't know how to do it, hopefully you could see how following the same method, maybe get to this bit is a bit tricky and going through this. But as I said, if you've got any other ways of factorising this quartic, please do let me know, but I think that's quite a good idea to follow. And it does help you to find out when you are solving, does help to link into your knowledge of solving matrices with quartic solution, or whatever it was that video called. Okay, so thanks for watching, hopefully it's been helpful, and we'll see you in the next mathematical induction video.